Okay, class, today we're going to do one more example for the finite element solution in 2D. It's problem 8.4 in the book with just a slight change. We have a constant temperature of 5 degrees centigrade applied at the bottom of the domain, and we have two flux boundary conditions in this edge and this edge. Both have flux of 10 watts over meter, and then we have the conductivity of the material is 2 watts over degree centigrade, and we have a source term in the entire domain which is 10 watts over meter square. And I think that's about it. So the first thing that I want to do this is to create my mesh, and in this case we're going to have a single triangular element, and I'm going to number the nodes with essential boundary conditions first. So this will be node 1, this will be node 2, and this will be node 3. And that's all I need because it's a single element. So element, node 1, node 2, node 3, a single element. And then for the connectivity, just remember to number the nodes counterclockwise. So in this case I have 1, 2, 3, 1, 2, 3. So the order is the same. So that's the first thing. Then the second thing that I need to do is to assemble the stiffness matrix. So for element 1, the stiffness matrix is given by the integral over the triangle of B E transpose times the conductivity matrix times BE integrated over the domain. Where remember, this is the general definition, so this works for any type of element. In this case, for triangular elements, linear triangular elements, BE would be the matrix that has the gradients of the shape function. So this would be the gradient of the first shape function, so both derivatives with respect to x and y. Second and third shape function. Again, note that this definition of the stiffness matrix is the same for any element. For the linear triangular element, we have 3 nodes, so we have 3 shape functions. Furthermore, because we can write out the expression of the shape functions directly in terms of x and y, we can actually compute this without the Jacobian or without the parent domain. We can directly compute this. This might not be true for other elements, but for the triangular element it is true that we can easily calculate the B matrix. So this is 1 over 2 times the area of the element, and I'm just copying it from a previous lecture. So this is y2 minus y3, x3 minus x2, y3 minus y1, x1 minus x3, y1 minus y2, and then x2 minus x1. Once again, this definition is the same no matter what element type do you have. In this case, for the linear triangular element, this B matrix, which has the gradients of the shape functions with respect to x and y, only has 3 columns because there's only 3 functions, and furthermore, because we can write out the expression of n1, n2, and n3 directly in terms of x, y, then I can compute this B matrix. In other cases, you might not be able to get this nice expression, and we'll do some of those in the future. But for now, for the linear triangular element, this is what we have. So in this case, I need x1, y1, x2, y2, x3, and y3 for this element. And for that, let me just draw the element again here. So here there's also a distinction between the local known numbers and the global known numbers. So 1, 2, and 3, that is given by this guy right here. So those are the ordering of this will give us the local known numbers. Sorry, these are the global known numbers. And in this case, the local known numbers are also 1, 2, and 3. So I'm just going to put a different color, but they are, in this case, they are the same. So local, global. So the global numbers are given by this, the mesh definition, and the local known numbers are given by just, they are always 1, 2, 3. In this case, they are the same. So x1, y1 will be 0, 0, x2, y2 will be 0.5, 0, and then 0.5, 0.5. So using these values, I can actually get the B matrix for this element, and I can calculate the area. So I can find that the B matrix for this element is minus 2, 2, 0, minus, 0, minus 2, 2. Again, I just used this definition, calculate the B matrix. Lastly, we also need this conductivity matrix. Because the material is assumed isotropic, then this is just going to be K times the identity, where K is 2. So this is just 2 times the identity. So that if I plug this value of D, this B matrix, put it in there, and then I do the integral over the triangle, I'll get the stiffness matrix. Again, there's some more simplifications that we can do. For the linear triangle, BE, well, D is not for the linear triangle, but in this case, because D is a constant, BE, in this case, is a constant. Which means that for the linear triangle, we can express the integral over the triangle as we can take everything out of the integral, and then we are left with the integral of d omega, which is just the area of the triangle. And so finally, we don't have to do any integral, we just end up with this, area of the triangle times B transpose times D times BE. Again, this is true for this particular case because everything is, all the gradients are constant, so we don't need to do actually any integral. Otherwise, you will have to do Gauss quadrature to integrate this. But in this case, we don't. We just do the matrix multiplication, and you can find that the KE matrix that we get from here is 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. You can check that for yourselves. And then we need to assemble into the global K. For that, what we're gonna do is we're gonna write our global node numbers here as always. In this case, you can see that there's nothing to do really. So the global stiffness matrix is actually the same. But you know that in, for example, the example that I did last time, then it had more nodes, so the global stiffness matrix was bigger. But in this case, they are the same. So, all right, that takes care of the stiffness matrix. Then the next thing that I would like to do would be force vector due to source term. So for element 1, the source vector, the general definition would be the integral over the triangle of the vector of shape functions times the source term. And then for the linear triangle, this has 3 entries because there's 3 shape functions. So this would be n1s d omega, n2s d omega, and 3s d omega. And here, because s is constant, then I can take it out of the integral, and I'm just gonna end up with integral of n1 d omega, integral of n2 d omega, put the e, integral of n3 d omega. And if you recall what I did last time, these integrals, if you just need to integrate the linear shape functions over the triangle, that's actually just area over 3. And you can go back to the previous video to see why that's the case. So this will end up being just s times area of the triangle over 3 times 1, 1, 1. So in this particular case, that is 0.4166, if I did this correctly. Again, this is the general definition true for any element. For the triangular element, I have 3 shape functions, so this is what it would look like. Then furthermore, because s is a constant, I can take it out. And then this integral of the shape functions, I can compute actually without doing the integral. So just believe me that it's area over 3, so I can compute that. And then if you need to do the assembly, in this case, you get the same thing. So again, put the global node numbers right next to here. In this case, fs, the global is the same as fs of 1 because there's just one element. Okay, so that takes care of the source term force vector. Then let's do the flux force vector. That one for element 1. So fq, what is the definition? The definition is integral over gamma q of shape functions times q bar. So in this case, it's integrals over edge because it's integrals over part of the boundary. And then the only boundaries that count are the ones that have a flux applied to them. So in this case, there's 2 edges of the triangle that have a flux. There's this edge, the vertical edge here, and then there's also this other inclined edge. Let me just call it left and right. So there's 2 edges that I need to do. I need to do integral over the right edge of n times q bar over the right edge plus an integral over the left edge I guess it's top left edge of this vector NE times the Q bar over that edge. So if I write this out, and again, this definition is true for any element. I need to see what edges of the element have a flux applied to them, and then those are the ones that matter. All the rest are 0. So here this will be integral over right edge of N1 EQ bar. And then I'm just gonna copy this. And I have 3 shape functions. So that's one, and the other one will look exactly the same. The only thing that I need to change is the edge that I need to integrate. Top left, top left, top left. So I need to do these integrals. Now again, because Q is constant, I can take it out of the integral. So I can just have basically Q bar times, and then these are just going to be, I'm just going to abbreviate that as right edge and RE. So this will be N1E and 2E and 3E. Plus basically the same, but I guess it's top left edge of N1E and 2E and 3E. And how to set up those integrals, that might be a tricky thing, but it is actually for the triangular element that's fairly simple, because let me draw the triangle here with nodes, local nodes 1, 2, and 3. Let me use the coloring for the local nodes. So the first one, which is the right edge, is this one right here. So I need to integrate shape functions over this edge. So let's look at shape function 1. So this will be N1E. N1E is 1 at node 1 and goes to 0 at the other nodes. So the integral of N1E over the right edge is going to be 0. Then I'll just make this a little bit small, and then so then what happens with N2? N2 is 1 at node 2 and then goes to 0 at the other nodes. So N2 looks like that. But in particular, I'm interested on the integral of N2 over this edge. So I'm really interested in the area of this triangle. So integral of N2 over the right edge is just going to be the length of the edge over 2. So this one is going to be the length of the edge over 2. And finally, for N3, N3 is 1 at node 3 and then goes to 0 at the other 2 nodes. So that's N3. And in particular, I'm interested in this triangle right here, because I'm interested just in the integral over this edge. So the integral of n3 over the right edge is just going to be the length of the edge over 2. So this one is also the length of that edge over 2. I would say right edge, right edge. So this one will be q bar times 0, length of right edge over 2, length of right edge over 2. And then for the other one, this is the top left edge, and I can tell you that shape function 1 is non-zero over that edge, so I can tell you that this will have length of the top left edge over 2 for the shape function 1. You can see here that that function is not 0 over the edge. You can see that this function, function 2, is 0 over that edge, so here I'm going to get 0, and then here I'm going to get length of the top left edge over 2 as well. And if I did this correctly ahead of time, then this should be 3.53, 2.5, 6.03. You can check the calculation. So that will be FQ for element 1, which is the same as the global force vector. Alright, so I have my source term, my flux term, my stiffness matrix. I can put together my system of equations. So that's K matrix times the degrees of freedom equals minus the FQ term plus Fs plus the reactions. And then so this K matrix is 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1 times the temperature at node 1, temperature at node 2, temperature at node 3 equals minus FQ, so minus 3.53, 2.5, 6.03, plus the source term, which was 0.4166, plus the reactions. And then for the reactions, I need to see which nodes have essential boundary condition. The nodes with essential boundary condition is this edge right here, so both first and second node have reactions. So this will be reaction 1, reaction 2, 0. And that's it. This is the system that I need to solve. Which ones are the unknowns? The unknowns are this right here, and this I actually know. So this would be, let me put it in green. So T1 equals 5, T2 equals 5. So these are the essential boundary condition. So those I know. How to solve the system? I could partition, and I uploaded code that basically partitions the system. So you get one single equation for T3. If you solve the last equation, you can solve for T3. And then if you then plug in this value, you can evaluate the first two equations to get the reactions 1 and reactions 2. So solve, for example, matrix partition. That would give you T3. Then plug in, and you can evaluate R1, R2.